processing archivist at Hesburgh Libraries at the University of Notre Dame, where she heads the team responsible for archival collections and management across 3 repositories. Jennifer holds an MLIS from Wayne State. This presentation will discuss experiments with custom AI agents designed to expedite archival processing by facilitating production of ArchivesSpace-ready metadata from a range of structured and unstructured data sources. The first agent, an archival metadata parser, was trained on ArchivesSpace procedures as well as national and local standards in order to generate Archival Object bulk loader metadata from scanned paper images. The second agent, a resource description generator, supplies a resource level description based on a collection inventory. A third agent encodes resource EAD from collection documentation. Jennifer will include discussion of the training data selected, experimentation, and feedback related to prompt and agent engineering, quality analysis of the resulting metadata, and future directions.
Hello, and thanks to the ArchivesSpace team and nurses for this opportunity to discuss some practical applications of generative AI in ArchivesSpace-related workflows. I'm Jennifer Recca, and I'm pleased to be here representing an amazing team at the University of Notre Dame Archives and the broader Hesburgh Libraries. I'm excited to share several ways we can explore AI to enhance technical processes. Sure. This is better? Yeah. Okay. All right, to provide a bit of context about the why for this line of investigation, I've long been intrigued by the potential for AI to someday help extract entities and relationships in our current finding aids, which are human readable, but not marked up, though present in long strings, for future linked data applications. So the parsing experiment was a way to sort of dip a toe into that water. That is, if AI can be trained to map archival relationships from a PDF of a TypeScript inventory, it might also be able to be trained to parse entities and relationships present within titles or scope of file notes or future semantic applications. Further, given that, as we know, archival metadata is complex, with relationships expressed both within and among individual fields and throughout the hierarchical structure, these experiments also provided a chance to see how well AI might encode or extract meaning represented within hierarchies. In this frame of mind, I attended a set of local workshops at Hesburgh Libraries focused on practical AI applications in the spring of 2025. Their attendees were challenged to identify a project and bring it to a workshop, and this parsing idea seemed like an interesting choice. So I teamed up with my colleagues, Sarah Joswig and Jason Kaufman, who identified a legacy sample inventory to parse. Our collective discussions on the topic flowed from there. And then, encouraged by initial results with regards to AI-mediated parsing, I looked at a couple of additional applications for AI to assist with metadata workflows. So the material that follows here is a look at 3 custom agents for experiments related to 3 distinct processes. Naturally, this work excuse me, that took place within our institutional AI landscape, and we were using approved AI products in compliance with overall campus AI policy. This in turn shaped the choice of AI tools and the scope of our experiments. Approved AI platforms at Notre Dame include Google Notebook LM, Google Gemini, and GTP EDU. We have a centrally managed process for reviewing AI tools and centralized data policies on campus. From this field of available tools, I choose to use the Gemini 2.5 Pro instance. In our local application, data supplied by Notre Dame does not train broader Gemini models. And it allows for domain-specific training through custom agents that Gemini terms gems. Gems have 3 components: a name, instructions, and knowledge. And that knowledge is the training data that you supply. Also of note, our institutional implementation of Gemini is approved locally for use with sensitive data, up to and including FERPA data, but only public data was used for this project. And so while Gemini gems are custom agents, and we're really discussing supervised learning in the archival context, this tool is really accessible. And it's free, though the chat generations on the 2.5 Pro model interface are limited each day, and I had to sort of meter my asks. So a little housekeeping. You won't need to access the drive linked in the QR code here to follow my talk, but if you're at all interested in some sample input or output data and the very basic prompt library I was using, that data can be found at the code here. Further, if you've never worked with Google Gemini, it's found at the diamond-shaped icon, which is located through the 9-dot navigation symbol within Google Suite. Once you're within Gemini, you can build your own gem, custom agent, by navigating to Explore Agents, and then selecting New Gem. You'll need to provide a name and agent instructions. Gems are trained as simply as just pasting the file path or dragging and dropping desired training data. This is a remarkably low barrier to entry. So the overall goal here is to understand the limits of AI in automating archival metadata tasks in a field where we contend with considerable backlogs, capacity limits, and manual processes. Every cell of data created represents both a victory and an opportunity cost. So I felt any effort saved is capacity one, and I investigated 3 key areas. First, understanding data parsing. Could AI reliably extract structured metadata from raw information? 2, resource-level metadata generation. So presented with a collection inventory, could AI be trained to automatically generate standards-compliant descriptive summaries? And third, EAD encoding from templates. Could AI encode EAD from existing templates to streamline the ArchivesSpace data entry process? Overall, the aim was to see if I could achieve predictable outcomes for rote or repetitive tasks that often intersect with more complex sense-making that is the domain of the archivist. The goal of the first experiment was to train AI to automatically parse unencoded archival data into standardized ArchivesSpace-ready formats. Manual parsing can be very tedious. It's hierarchical, it's granular. Commercial AI parsers do exist, largely for business data, where relationships tend to be more linear. Think about invoices, payroll, customer data, and where the vocabularies, the labels that you're trying to apply to parsed content tend to be much more universal. So a custom parsing solution I felt was needed to properly bucket and classify the information from unstructured sources into the formats required by ArchivesSpace. So a couple of examples. The image on the left shows an example of data to parse. Here it's just a snippet of a collection inventory sent to me through email by a curator. You add these 20 items to a finding aid. The second image is a bit of a typescript of a collection inventory that was generated by a repository in the 1970s. While these examples are neither extensive enough or well-structured enough for rules-based mechanical parsing with a script, I was curious how well AI could fill that gap. A note on the process. So the development of this experiment involved a cycle of testing, analysis, and refinement. That iterative process was key to improving output. And it was true of parser, and it was true of all the subsequent explorations. So initially, I created an all-around processing archivist, gem, or agent, thinking it could assist with a wide range of tasks. I had some initial successes, but the results were really inconsistent. So I created a gem that was my, it was a assistant, processing archivist, all kinds of data and standards, and thought I could use it for all-around help. But there were some frustrating failures with the approach, such as the AI agent alternately beautifully completing the AO loader template one day, and then the next giving the same data and prompt, telling me, I can't help with that, I'm a large language model, the next. There were also frustrations with chat and associated data loss. So to address these issues, I created several discrete agents, coding training data, prompts, and agent parameters with much more specificity, and this yielded a much more precise output. Developing dedicated agents and crafting and tracking prompts through a simple library, really just a Google Sheet with tabs for agents and prompts and links to chats, was important for improving my results. So, how was the parser built? For each of these experiments, there are several moving parts. The gem or agent instructions, the training data, and the chat prompt. A fourth variable to consider is an input file, which can be acted upon in the prompt, supplying data that is acted on in the course of the execution. So first, the agent instructions. The agent is told explicitly, the goal of this parser is to take unstructured data about collections and then turn it into structured tabular data that I can use to build a finding aid. The agent instructions had to be this prescriptive for the gem to know it was meant to use its large language abilities to classify and map existing information, not generate new content. Second, training data included national and local standards, blank and populated loader templates, and local instruction guides. In the third column here, the prompt established further guardrails, including marking, handling for markup and syntax, how to format component unique IDs, and I found that directly listing the desired loader headings was the most consistent, generated the most consistent output. Otherwise, if I just said, take the data and fill out the template I gave you with the training data, things got a bit fuzzy and drifted a bit from the format I really wanted. As Gemini can't write directly to sheets and docs, I requested the formatting of the final output in TSV, and this could be easily cut and paste into Sheets or into Excel. So here's a sample of the data output by the parser. The input was the Richard Sullivan inventory PDF from 1970, which we saw a few slides back. A full copy was available in that mini drive. So you can see that in one iteration, we've gone from an unstructured TypeScript finding aid to something very easily wrangled into the ArchivesSpace AO loader. Gemini alternately struggled with the concept of the multi-row header for the Archival Object loader. So the data in the header rows would have to be added for ingest, along with the other editing, but that's not really such a big hill to climb. So the ups and downs. The parser was able to successfully convert a semi-structured list into structured, almost system-ready format. This validated the idea of using generative AI for archives domain-specific data structuring. The parser had modest success in encoding hierarchical relationships, and it accurately transcribing that date information. It did a really good job of extrapolating date begin, date end from data expressions, and it put all of the above in the right columns. However, the parser had some limitations. It produced incorrect information, such as container instance type, and missed a couple of hierarchy cell levels, or level cells. There was also complete redundancy between the title and scope note in a couple of cases, and it used abbreviations we might not use today. Importantly, it also stopped processing at box 6 of a much more lengthy inventory. So I didn't have full coverage of the data set. Overall, and when I would ask the chatbot, hey, you stopped, you're doing a great job, I said, I'm sorry, my mistake. let me fix that for you, and it would maybe do 20 more lines and stop again. So I'm not sure if that was a tokenization issue or what the challenge was, but yeah. Good with a short inventory. So overall, this demonstrates both the potential and current limitations of using AI for this task. We've got some thoughts about addressing these limitations in the next phase of the project. All that said, technology like this could provide a meaningful head start if the input inventory is for unprocessed material, and it could rapidly expedite translation of paper finding aids for processed material into ArchivesSpace-ready metadata. So a bit encouraged, I became curious about what else might be possible. Experiment 2 explored using AI to extract data from collection inventories. I tried both the loader sheets and the scanned PDF from the last experiment to generate standards-compliant resource-level summaries. That is, the notes, the agent headings, and the subjects. There are likely different approaches, but at Notre Dame, our process is to compile the inventories in the Archival Object, both loader sheets, as we perform the physical processing of collections, and then to draft notes and headings in a Google Doc prior to transferring all of the description into ArchivesSpace to build a finding aid. And here was to learn. Provided with collection inventory, AI could provide a jumpstart drafting the collection level description document and thereby reducing overall time needed to complete that task. This was a big philosophical departure from the last exercise. Here I did want AI to generate new text rather than parsing and transcribing supplied text. The agent instructions, the training data, and the prompts were customized to that end. So structurally, this is what that looked like. The agent instructions are tailored and include the term supply, that is, I want you to make something. The training data for the description generator includes resources like DAX, local description templates, and sample notes to inform the construction of each element. The prompt also gives specific instructions to review an attached inventory provided in the prompt, summarize it in a template, document template, and to follow the rules and samples in the training data. There are also instructions guiding vocabulary choices for the controlled headings. Here again, the data is asked for in a format readily copyable into a document. The input file attached to the prompt here was again the Richard Sullivan Papers PDF inventory, that 1970s TypeScript version. So this slide shows some samples of output from that description generator, gen/agent. The bio and scope notes were pretty well formed and accurate. The bio note appears to be a summary of a Wikipedia article. And even if some adjectives are slightly more laudatory than I might prefer, I think it did a reasonably good job. However, the AI agent hallucinated provenance and got it wrong. It also likely hallucinated every materials note, but did get it right. In the second image, the controlled headings are almost entirely valid, save for the geographic subdivision under Catholic authors. I had to look that one up. Small point, I'd probably add a few headings, but I think overall I was really surprised at how good the subject analysis was. So now we come to the third experiment, an EAD builder. This was just a check to see how well, considering the formidable sort of coding abilities that these chatbots have. It was a check to see how well an AI agent could encode EAD when fed the type of resource description Word documents we just discussed a moment ago. So, aim was to rapidly convert semi-structured resource description in a doc into importable EAD. I was just curious to know if an EAD file could be reliably written by AI, and if it would be well formed enough to be ingested directly into ArchivesSpace. The thought being that this would streamline data entry and the creation of component records. Though, of course, the control vocabularies would need to be, subject and agent records would need to be manually decoded or, imported and merged. So it's an idea with limits, but perhaps some utility. Here's an outline of specifications for the EAD Builder agent. It describes the agent's role in taking structured data about collections and transcribing it into valid EAD metadata. The agent is instructed to use your generative abilities to code and map, not generate descriptive text. The training data provided includes sample EAD finding aids, EAD documentation, and a text version of the archive